I recently posted a video on spring reverb in which I examined the construction of a reverb tank and then measured its impulse response and frequency response. I don't want to repeat all of that here today, so if you're interested in learning more about spring reverb, you can check out that video later. But just briefly, a reverb tank is a sort of electromechanical delay line used to simulate the echoes that occur in a large space like a concert hall. And it does that by converting an electrical signal into mechanical waves that travel through the springs. So at the input end, there's a transducer which converts the electrical signal into mechanical motion of small magnets that are attached to the end of the springs. And one of the things that people seem to be surprised about in the last video is the fact that the motion of the magnets is actually torsional and not transverse, as say in the case of a guitar string. I have to admit I was a little surprised myself when I learned that fact. And then several people asked if it's possible to actually see the motion. Well, the short answer is that under normal conditions, you can't see the motion, but with a few tricks, we can see it. So the reason we can't see the motion under normal conditions is that the displacement of the spring is just too small to see, at least at normal operating frequencies. But by lowering the input frequency, we can increase the displacement to the point where it does become visible. But there's a few problems when we try to do that. So in the earlier video, I was driving the reverb tank with the Fender guitar amp that it came with, and there's some preconditioning circuitry that exists in the amplifier, between the input to the amplifier and the input to the reverb tank. And part of that circuitry is a high-pass filter at about 100 hertz that prevents anything below 100 hertz from going through the amplifier and the reverb tank. And the reason for that is that anybody who's played around with an amplifier with a reverb unit knows that anytime you bang it or anything like that, that the tank will respond and make a lot of noise because the springs will pick up the vibrations. So in order to reduce that kind of susceptibility, they basically cut off all those low frequencies. Otherwise, it would be even more susceptible to that type of problem. So now also in that video, we measured the response of the system as being between about 100 hertz and 7 kilohertz. And it turns out that the top number, 7 kilohertz, is the actual high response of the tank itself, but that the low number of 100 hertz, that was actually really just a limitation of the amplifier and of the high pass filter in the Fender amp, and not a limitation of the tank itself. The tank itself can actually respond at lower frequencies. So what I've done here is that I've dispensed altogether with the amplifier, and I'm driving the tank directly from a signal generator. And it turns out that we need to get down to about 5 hertz in order to get the maximum visible spring displacement. And so the generator is set to a sine wave at 5 hertz, and it's got the maximum output of the generator that it can produce is 20 volts peak to peak. But the generator actually has an output impedance of 50 ohms, and the input transducer, it's rated at 600 ohms, but that's at 1 kilohertz. So at 5 hertz, the impedance of the transducer is pretty close to the DC resistance of the coil, which is only 58 ohms. So we don't get 20 volts at the input to the transducer. It's more like about 10 or 12 volts. But anyway, it turns out that is just about sufficient to drive the coils to the point that we can see the motion. So let me get in here and see if it's visible. I'll zoom a bit more. Now I've painted some marks, some small white marks onto the magnets to make the motion more visible, but you can just about see the motion here. And I've actually got a DSLR with a macro lens, which I'm going to try out in a minute here, and we'll see if we can get an even better view. This is my D7100 SLR, and it's actually an older camera. I've had it for 10 years, and the model is even older than that. But because it's an older camera, at 60 frames per second, the resolution drops down to 1280 by 720, which is fine for this purpose. But I've also got a macro lens, a 60 millimeter macro lens, which I've had for about 35 years. And in addition to the macro lens, I've got a 36 millimeter extension tube. So the combination of the macro lens with the extension tube gives a total magnification of about 1.6. So that means that the image on the sensor itself is 1.6 times larger than the object in real life. But the problem with macro photography is that because you're looking at such a small area, that there's very little light available, and so you need to have a good strong light source. The other problem is that with macro, that the depth of field is very shallow. So if you want to have things in focus, you actually need to shoot at a small aperture. So I'm shooting at f/22, but that makes the problem of light even more problematic. So I'm shooting at f/22 at 2/50th of a second, and even with that strong work light that I have here, I have to go to about 6400 ISO. So anyway, let's take a look through the camera and see how that works. So this is the view through the macro lens, and as you can see, the motion is quite a bit more visible now. We're still at 5 Hertz, but I'll change the frequency and we can see the effect of that. So we're at 5. I'm going to step down to 4, 3, 2, 1. I won't go below 1 Hertz as the motion starts to roll off below 1 Hertz. But let's go back up again. So we're back at 5 and going up from there. 6, 7, 8, 9, 14, 15, 16. Now you can see at 16 Hertz, the motion is actually chaotic. I guess due to the large number of reflections, the whole system can become chaotic at certain frequencies, and it appears to be chaotic at 16 Hertz. Let's go up a bit more. 18. So at 18 Hertz, this is another interesting effect. So I guess you can't see it in this view, but the springs are kind of shaking overall, and the springs are actually attached to a platform, and that platform is separately sprung from within the case of the tank, and I guess the purpose of that is to provide isolation from vibration. But in this case, the motion of the springs is actually causing the entire platform to vibrate, which is why you see that shaking. Going up from there, 20, still shaking at 20, 21, 22, it stopped shaking now, 3, 4, 5, 6, 7, doesn't seem to be much motion, so I guess the motion is now less visible at the higher frequencies. 30 Hertz. 30 Hertz, I won't go beyond 30 Hertz because the motion would be aliased, because the frame rate's only 60 Hertz, so it'll alias above 30 Hertz. If I just go to, well, there's 33 Hertz, or 32, there's 33 Hertz. And you can see, it does appear to move, but it's actually just aliased. So, let's go back to 5. Anyway, so I hope that answers the question about whether or not you can see the motion of the springs in a reverb tank.